Welcome, everyone. My name is Gianmarco Iodice. I'm the chair of the tinyML Global Meetups and also the tech lead for machine learning software library at Tarn. And today I have the great pleasure to moderate this talk where Matthew Stewart from Harvard University is going to talk about datasheets for machine learning sensors. And I'm very happy, honestly, to moderate this talk because one of the definitions for tinyML is actually a layer on top of sensors. And today with Matthew's presentation, we're going to discover more about this definition and what it means actually in terms of datasheets. So before we start with this session, let's go through the initial introduction. So let's wait just a few seconds so I can control the slides. Okay, so before definitely we start this presentation, we need to thank all the tinyML strategic partners which are making all these tinyML global meetups and events free. So in particular, we want to thank AZ, Analog Devices, Arduino, ARM, Brain, Edge Impulse, Green Waves, Gravity, IBM, ImageMob, Infineon, Inotera, Microsoft, Not.ai, NXP, Polycon Technology, Kixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microtronics, Synaptics, and Synchance. So thanks to all the tinyML strategic partners that are making these sessions free for all of us and the tinyML community. So the other thing I want actually to share with you is a few numbers about the tinyML Foundation, tinyML community. The community is growing worldwide because now we have reached 49 groups in 41 countries. We are almost there to the first milestone, 50 groups in definitely all over the world. We have definitely more than 50,000 members in that join the tinyML meetups, and definitely you can learn more by subscribing to the link reported here, but also joining us on LinkedIn, where you can find the community sharing their posts and sharing news about what is happening in the tinyML world. So this presentation, as many others we have delivered so far, will be definitely on YouTube. So you can watch it for free. It's going to be available in few days. You can only need to subscribe to the tinyML YouTube channel to have updates and notifications about also future events and future presentation we're going to host for the tinyML global meetups. Just to give you some numbers, we have roughly 10K subscribers with roughly 600 videos hosted. So definitely this is super there. And this is also a demonstration of how active is the tinyML community in sharing the knowledge and spread the knowledge about this fascinating world, which is an intersection of hardware, software, and also the sensors. This is almost your turn. Matthew, I'm going to present you. So Matthew Stewart is a postdoctoral researcher in the Edge Computing Lab at Harvard University. He holds a PhD and a master's degree in engineering science and data science from Harvard University, and integrating bachelor in mechanical engineering from Imperial College London and the National University of Singapore. Matthew's research work is highly interdisciplinary, encompassing embedded machine learning, autonomous vehicles, benchmarking tools for reinforcement learning and robotics, sustainable computing, and machine learning sensors. Matthew is also a part-time blogger towards data science and co-creator of the Harvard X tinyML courses and the research coordinator at ML Commons. So thanks a lot, Matthew. So we're super excited to learn more about your presentation, in particular to learn more about datasheets for machine learning sensors.
Thanks, Gian. Yeah, and thanks everyone for coming. It's great to see such a turnout for a topic on datasheets. I know it's like a riveting topic for most people. So yeah, I'm going to walk through kind of an introduction to machine learning sensors for those of you who maybe aren't so familiar with it, and then go into sort of specifics of what a datasheet might look like for sort of the tinyML ecosystem. So that kind of analog of the hardware datasheet that we see traditionally, sort of superimposed on the tinyML domain. So in the past few years, we've seen, initially we had stuff going, the machine learning models on data, running in data centers. And since then, we've seen sort of a bifurcation in compute. So we've seen companies moving towards larger and larger models. We have language models now that are in the sort of billions and trillions of parameters. And then we've also seen the other end, which is, trying to get these models and compress them so that they can fit on smartphones. So now we have small language models that fit on smartphones, and we have IoT devices which act as a gateway to the cloud and give some sort of pseudo intelligence. And then obviously everyone here knows that even more recently we've seen this sort of embedding of intelligence onto these kind of embedded devices, and this offers us a lot of new opportunities. And now we're able to do machine learning at the level of an individual sensor, which opens up a very wide array of opportunities for us. And one of them is just that this kind of extreme edge where the sensors are is where the data is created. And generally speaking, most of that data is underutilized. And so if you're able to sort of capture that information and provide actionable outputs from it, then there's a lot of use cases and opportunities that might arise from that particular capability. And so we're kind of used to this traditional tinyML paradigm where we have some kind of sensing device, it transmits raw data to a processor, and then we load and run some model on it, some on-device model, and then we send that data to the cloud, or we do some actionable outputs with it. And we've kind of, in our lab, we kind of call this the sensor 1.0 domain. This is basic cookie cutter stuff. And there's a lot of issues with this particular way of framing this domain. The first one just being that you can imagine here we're transmitting raw data. And so depending on what this information is, if this is taking pictures of me as an end user and it's transmitting raw data, this has some privacy implications to it. Same with transmitting it to the cloud. It could be intercepted by someone. So there's also security implications as well. There's also other aspects such as I don't necessarily know what's going on inside this device, but other than what the manufacturer has told me. And I also have no reason to trust the manufacturer because there's been no kind of, there's no hierarchy of trust that's been created in this particular ecosystem. And then also from the device manufacturer's perspective, so basically all of these aspects mean that we don't really, that there's some problems that have been presented with this, and these have come to the head in the media a few times. One of the most sort of prevalent that you might have heard of is people finding a microphone in their Nest thermostat, and naturally you would ask, why is there a microphone in my thermostat? And so this gives people sort of a negative connotation to these types of devices, thinking that they're spying on them or extracting data that they shouldn't be. And so the question is, how do we architect future tinyML devices so that we kind of prevent this from happening in the future? And really that means sort of addressing the privacy implications, addressing the security ones, but also transparency. How do we empower end users so that they are able to sort of know what's going on in these devices and what is happening with their data? And this is where the idea of the machine learning sensor came in, which was developed by Pete Warden, who is one of our collaborators. He worked at Google and now he's doing his PhD in Stanford, and he has a startup developing these types of sensors. And so this is the first ML sensor on the left that was developed by his company. But the way we've described sort of what an ML sensor is we've coined it as a self-contained system. So self-contained meaning it's in a single package, in the same way that you might buy like a temperature sensor or anything like that. It uses on-device machine learning. So this is the tinyML component. And it takes useful information by observing some phenomena in the physical world. So this is kind of the sensing element to it. It's taking this information and performing some actionable output, and then it reports it through a simple interface. And the word simple here is kind of key because the way these sensors, at least the way we've developed our sensor, is sort of by a privacy and security by data abstraction. And so simple in the case of it is what we are sending is simple, but also it's simple in the sense of abstraction of the data. And so what does this actually look like in comparison to the traditional domain? Well, basically we take the physical sensing element and we take the processing element and we just kind of squish them together onto a single package, which looks something like this. And so you can see here we have, this is doing, so I'm going to be talking a lot about person detection. That's the case study that we've been developing recently. And the idea of that application is it takes a picture of me as a person or of a scene, and it says, is there a person in this image or not? And the answer is either yes or no. So it's a binary classification problem. And obviously you can imagine, like, if I'm sat at home in my house and I have a TV that's taking pictures of me just because it wants to know, am I watching TV or not? It seems like a pretty normal application, but there's actually a lot of information embedded within that image that you don't necessarily want that manufacturer to know. For example, they could learn like about your family, sort of your ethnicity, how many children you have, your socioeconomic status. And if the only reason they were doing it is to know if you're watching TV or not, or something like that, then it's a lot more information than they require. So if you're able to limit that through some sort of data minimization scheme, you add some sort of power back to the end user here. And this is kind of what is going on here. So it's taking a picture of this person running through a model which is inside the sensor, and it's sending high-level information through to an application processor, which could be, something that the sensor is connected to, like a Raspberry Pi. And then the rest of the system is basically the same. You could send it to the cloud if you wanted to, but all the interesting stuff is happening here. And so we don't really care exactly what the architecture of this sensor looks like under the hood, because there's various ways that you could instantiate this. We put a lock and key around this because you could have, for example, like a secure enclave if you wanted it to be, very secure, the data movement going around on the device. And then we've put here a data sheet. And the reason this can have a data sheet, whereas the traditional ecosystem can't really, is because this is a sort of self-contained and modular device. Like I can go and buy one of these, where it's harder to go and buy, like an embedded system which has all of these other functionalities when it's not in sort of a sensor packaging format. And this offers various benefits. If you have a data sheet, for example, an end user can go and read it and say, okay, well, does this device have a microphone in it? And they would know off the bat. They wouldn't have to go and find out in the media 6 months later when someone finds a microphone. And then it also fosters trust, because if you have a third-party entity that takes that data sheet and then goes through and verifies that it is correct, you have some sort of verification from a trusted entity that the end consumer can then go and say, okay, I actually believe that this is correct. And it also gives them information of, now I know what the device is doing. And from a developer's perspective, they don't have to know anything about machine learning necessarily to be able to use these devices, because it's sort of abstracted behind this barrier. And so we've developed these 5 guiding principles for sort of how should you develop machine learning sensors. I'm just going to briefly run through each of these and then get into the data sheet aspect. So the first one is the level of abstraction. So the idea that you shouldn't really have to be an expert on machine learning to develop sensor systems and devices that use machine learning capabilities. So for example, if I go onto DigiKey and I look at temperature sensor, there might be 10 or 20 vendors that sell different types of temperature sensor. And I can go through and look and say, okay, well, I want one that has this particular range, these characteristics. And the idea is that I could do the same for a person detector. I could say, okay, well, I want it to be for a large room that requires a large field of view. And I can go through and look at each of those and say, this is the one that's best suited for my application. And if I install that in my device, if it has a standard interface, there's no reason for me to know anything about machine learning to be able to use that machine learning capability. And so this makes it user-friendly for both developers and end users. And yeah, you could imagine going to any of these vendors that you might typically use and just buying specific devices for commonplace applications that people have developed. The second one is that it should be inherently data-centric. So, we don't really care what's going on under the hood in terms of the device itself. It's more, how is the data being processed and what does that input-output behavior look like? And so that's kind of one of the key focuses here. For the third one, this is kind of the equivalent of Occam's razor. So we want it to be clean and complexity-free. So, for example, if you're making a person detector, don't put a microphone in it. Like it's unnecessary, it's superfluous, and it's unjustifiable in this particular case unless you have some planned added functionality that you're trying to put on. And also you want to have some kind of standard interfaces for communication. So the idea is if I have 10 manufacturers and they all have a different way of doing data formatting, if I try and take a certain sensor out and put another one in, it's going to break everything. Whereas if they all speak the same language, there's some level of sort of interoperability going on there. And so this makes it sort of more reusable as well and more user-friendly. And then this is where stuff really gets difficult, which is how do you add transparency to the system? And the way that traditional hardware companies do this is they have data sheets. But the difficulty comes in, okay, well, how do I add that level of transparency to a machine learning enabled device? Because not only is there all of the hardware characteristics, but there's all of the machine learning characteristics too. And, in the machine learning stuff, there's a lot of things to consider. There's the data, there's the model, there's the performance in the real world, there's all of the mechanisms surrounding that as well. And so it's also not clear like why people might want a data sheet, but I think, we've kind of justified it already. You would want to know sort of what's going on in your device, and you would want to know how to interface with it and the characteristics if you were interested. The reason this project came up is because the professor I worked with, VJ, he bought a TV for his house, and he was doing yoga one day, and it said, do you want us to analyze your yoga poses? And he said, if you want to analyze yoga poses, you have to have a camera. And he went and looked at his TV, and he couldn't find a camera anywhere. And then we all had a laugh about it and said, well, if a professor who studies edge computing doesn't know his TV has a camera in it, then we're all kind of screwed. And so after that, we were saying, okay, maybe there needs to be some mechanism in place so that when people buy things like this, they know, what they're getting, basically. And so this is kind of what the datasheet template that we've developed looks like. So it has everything you would expect on like a standard data sheet, like diagrams, hardware characteristics, the communication specs and pinouts. And then there's some stuff we're maybe not too familiar with. So stuff like a data nutrition label, which characterizes the data set that was used to train the model. You're going to have the model characteristics themselves. So this is things like how well does my model perform on a test data set, end-to-end performance analysis. Now that means if I deploy that model in the real world, what does it look like? Is there any demographic biases? Is it affected by lighting? If I stand 5 meters away from it, is there a massive drop off in performance? Stuff like that. And then we also have privacy and security. If they are keeping data, how long are they keeping it for? What's the retention mechanism? And then we have things like compliance and also environmental impact, because people care a lot more about that these days. They want to know in the devices they're buying, sort of what is the impact of that particular thing, especially because in recent years, the embodied footprint has become more important than the operational footprint as these sort of processes become smaller and smaller and the amount of technology becomes sort of more energy consuming to develop those devices. And so I'm just going to walk through an example data sheet that we made for our open source person detection sensor, just to give you an idea of like, what does a data sheet look like? And so for here, we have, very standard things that you would see for a binary classification model. We have precision recall curves, ROC curves, confusion matrix. And this is basically just so that you can compare between different models if you go into their data sheets and say, okay, this one's better than this one. And also, you can tell, is there any sort of massive red flags? So in this one, yeah, 75% accuracy is not ideal, although we are running this on a Cortex M0, so don't have too high expectations. But yeah, we're not seeing massive false positives or false negatives, so there's no major red flags. And you can see here we have a bit of bias in this histogram of predicted probabilities, but there's nothing too concerning about it. And so this gives you kind of a holistic picture of what does the model performance look like, and you can also describe the model development procedure in detail in the datasheet. And if you want to see the example datasheet we have, it's on arXiv, and I'll give a link at the end of the presentation to that. For the data nutrition label, so this is taken from the data nutrition project, which developed first a semi-quantitative labeling system, and now it's sort of more qualitative in a sense. But it basically gives you high-level information about what does the data set look like that was used to train this model, in terms of like what's its attributes. This one, for example, was about humans because we're taking pictures of people. Was it developed from an upstream source? In our case, yes, because we were using the visual wake words dataset, and this was from the MS COCO dataset. Is there a technical review? In this case, yes, there was a paper on it. Ethical review, no, and also nobody's updating this dataset anymore. So it just gives you information about what does that workflow look like. We're probing this dataset prior to any sort of model development here, to assess for things like biases or even I remember in the MS COCO dataset, I was looking through it at one point and I found a picture of a horse that was labeled as a human. So, people have mentioned that there's quite a few labeling errors in that particular dataset. So that's something, if people know that that's the dataset that was used for training, they might be interested for that specific purpose. The next one is the privacy and security label. So this was from the IoT privacy and security project. And basically this is a very high level view of sort of what data modalities are collected on this device. So in our case, we only have a camera. So there's only one modality, it's an image. And we said that image is not stored, it's not sold, we're not retaining it in any way, but there's also no security mechanisms or updating of the model. So, there's pros and cons in terms of allowing updating or keeping the model very secure, but not allowing updating. And so this just gives you an example of what such a label might look like. This is some of the interesting stuff, which is the performance analysis. And so this is quite hard to characterize because we want to know, how does this device perform in the real world? You've shown in the model characteristics that we have a test data set that you might have curated, and we've said it has these particular levels of performance, but we don't actually know, if I put this in my house, how well is it going to perform? And so we had to develop an entire study environment, which I'll describe now. But basically this helped us assess, is there any demographic biases in the model? And also, how does it vary with just like environmental conditions? Because, especially for a person detection sensor, does it perform better during daytime versus nighttime? If I'm really tall or I'm wearing a particular type of clothing, how's that going to affect the model performance? We didn't do all of those variables, but you could imagine those impacting the performance, and that might influence the decision of whether someone wants one or not. And so we developed, we have this robotics testing arena that we turned into a data warehouse, basically. And we've got basically closed it off to ambient lighting with these curtains that block light. And we created a testing area, which is 3 different distances. So 1 meter, 3 meter, and 5 meters from our sensor system. And we tested 39 participants at 3 different lighting levels and those 3 different locations. And from that, we did 10 measurements at each location, and we averaged the results across those 10. And that helped us to work out sort of how the performance was per each sensor. And we had 6 sensors, so 3 from 3 open source sensors that we developed, and then we had 3 that were developed from a commercial entity called Useful Sensors. And yeah, so we had this neutral background environment with all these overhead lights, and we assessed sort of what the performance looked like across those domains. And the first one was we were assessing lighting, and we see that there's kind of a marginal decrease in the performance as we go to lower lighting levels. So 200 lux is like, kind of a dark bar, and 1200 lux is like a well-lit room, kind of like the one we're seeing in this image right now. And then distances, we see there's actually an initial increase in performance, and I think that's because maybe people were slightly obscured here because of the limited field of view of our particular sensors. And then also, we see a massive drop off as we go sort of above 3 meters, which is, interesting. It's probably because the person in the image was too small. There wasn't enough pixels for the model to really pick up there was a person there. And so you can imagine if you wanted a device that could see people sort of more than 5 meters, this would not be the one for you, or this is how you might use it, for example. We see a slight gender bias. It's not clear if that's like because of the data set that it was trained on or some other characteristic. And we see a similar bias for skin tone as well. So this is using the Monk skin tone framework, which was developed by Google to determine, and we categorized it into sort of light, medium, and dark skin tones. But we see, a sort of a drop in performance towards darker skin tones, and this might have been because of the sort of contrast between these black curtains here. But yeah, this just gives us an indication of, what does that model bias look like in the real world? We've also done this using confidence value instead of actual percentages, because depending on the threshold the user might want to set, it would change, the level of false positives and negatives. So if anyone was wondering why we did that. The next part of the data sheet is compliance. Obviously, you would care whether the model was, the device was compliant to particular compliance standards or, regulations, things like that. For example, GDPR, if it's not compliant to GDPR, that basically excludes you from using it in the whole of Europe. So, if you were a company in Europe, you would probably want to know that before you bought one of these devices. And then just things like, FCC regulations, does it have any lead in it, things like that. And so this helps sort of give users a greater idea of sort of the trust in the product's performance. If you say that its accuracy is 75%, is it actually 75%? And so it gives you sort of this buildup of trust, especially if it's verified by this third-party entity. And also it guarantees that there's some adherence to industry standards other than you just taking the word of the manufacturer itself. And then, the standard stuff that you would expect to see in a normal data sheet. So we have diagrams, form factors, so that people could know like how big it's going to be, how to communicate with it, stuff like that. Lastly, we have the environmental impact. So we developed a calculator for tinyML devices in particular to characterize their estimated footprint. And you can see for this particular device, the largest proportion goes to the sensing element, and that's because we're using a camera. And in the development of cameras, they tend to have a fairly large CO2 footprint. So this takes up about 1/3 of the total emissions. To give you an idea, this is about 2.3 kilograms is maybe 6 or 7% of the emissions of an Apple Watch, or 1/100th of a laptop, something like that. And you could imagine obviously having more than just carbon emissions in the environmental impact section. There could be things like water usage, eutrophication potential. You could have VOC emissions. There's many types of variables. These are generally more difficult to characterize than just the CO2 because you need a lot more information about the actual manufacturing process in order to characterize those. And so this gives you an overview of what our data sheet looks like. So we had this privacy and security element. We had this data nutrition label. We had our performance analysis. We had some model characteristics. We have these diagrams and form factors, and we have this environmental impact section. And so the fifth guiding principle is that, we really want to aim to foster this open source ecosystem for people to develop sort of their own data models and also hardware. So the idea, like we just developed an open source person detection sensor, but I'm sure, if we gave the open source community about 10 minutes, they'd probably make a better one than we did. So the idea of just building this up so that for the most common use cases in particular, there's actually great things in place that companies can just go and leverage, and also end users can leverage without having to pay through the nose for them. But also, without allowing like the relinquishment of intellectual property for companies that are actually trying to build devices like this in this space. And so we also developed a website for this, if anyone wants to go and look at. Also, the white papers are on this website. It's mlsensors.org. And so the white paper is our original ML sensor white paper, and the Datasheets paper is the one we recently released, which basically describes the procedure I just went through for us developing our own machine learning sensor and sort of how we went about doing that. And then appended to the end of that is the example of our open source ML sensor datasheet. So just to recap, the sort of principles of the ML sensor. So we had the abstraction. So we want people to not have to be experts in order to use these devices and develop them. We also want it to be fully data centric. So the emphasis should be on the data itself and the input output behavior of the device, not necessarily what goes on in the device, although if the person wants to, they should disclose that within the data sheet itself. The implementation, should be clean. We want to have Occam's razor, no mysterious microphones floating around. We want to have the transparency described within this data sheet, which is an analog to the hardware data sheet that we see with traditional hardware sensors. And then we want to foster that open source community so that we have lots of open source implementations for the most common applications. The most common of which that we've seen is person detection. And so the next thing we have going on is we're running an exploratory seminar to basically discuss, what are the ethical implications of ML sensors in particular? What kind of compliance standards should we develop for sensor developers and manufacturers? Do we need a third-party certification body? What are some other sort of characterizations we can make for these devices? And also, how should we develop this interface for communication across sensors and also other device manufacturers? But yeah, that's all I was going to talk about today. So thanks everyone for listening. If you want to go and read any of our papers, then go ahead and go to the website. We also have a GitHub page, and also feel free to email me with any questions. And also I'll answer any questions you have now, if anyone can think of any. But yeah, thank you for listening.
Thanks a lot, Matthew. Well, of course, they're going to have questions also because I have a question. But before, okay, let me see if I can still control your screen. Yes, okay. Okay, so let me go through in the Q&A tab and see what we have there. So I start with the first one. So what problem shifting compute to the sensor is trying to solve? Minimization of upstream bandwidth and local limited inference for offline users? What do you think about it?
Is there a way I can see the questions?
So it's in the Q&A session, in the Q&A tab at the bottom of Zoom. So I believe part of this question has been answered, I believe, during your talk, but I don't know if you want to expand a bit. So
yeah, so basically, it's kind of what I said. Like, it's not really so much of an engineering problem. It's more just so it's like it's more socially responsible in the sense of it's easier for me to self-contain things on one specific device than it is across multiple devices. If I have a sensor which has this compute capability on it, I can keep everything on that device, and I can, make it super secure if I want to. I can also, like you said, limit the bandwidth across from that particular sensor to the application processor. But I'm also doing this kind of minimization procedure, which offers the privacy security benefits and the level of abstraction that we provide by doing that has benefits in terms of user-friendliness and stuff like that. And you couldn't really, like, it also allows you to do the datasheet format. Like, it would be very hard to characterize a datasheet for a device that uses, multiple different sensors from other manufacturers and stuff. It would get very messy than just having like a single self-contained sensor. Does that kind of answer your question, whoever asked that?
I think so, but of course, Brian, you can write another question if you want, if has not been answered properly, but I think this has been answered. So there is a generic question. So how people can contact you to understand if they can collaborate on this. So by email, so how the people can contact you, Matthew?
Yeah, I'm pretty easy to find online. But yes, my email, hopefully, do you guys like send out my email, or I'm sure you guys have contact details you can send out to people.
Okay, sounds good.
Yeah.
So there is an interesting question. So what does the process look like for implementing the machine learning sensor in a project?
Where is this question?
So it's at the bottom.
Oh, okay. In terms of integrating an existing one or developing your own sensor, I guess it sounds like someone wants to know how to integrate it.
I believe so.
Yeah. So in terms of the TV example I gave, doing yoga poses or whatever, if you just had one that did pose estimation, and then it sent the labels for that pose estimation or whatever the output is, and basically just had some kind of software interface with the device manufacturer, they could just, through some API, ask it for the information, and then take that information and then, do whatever they want with it in the actual device. But the point is that it would be a third-party verified device where the user actually trusts the output from it. And you don't just have to necessarily trust, whoever made the TV and just take their word that they're not selling pictures of you for, the data brokers to extract extra information from you.
Okay, so thanks. Okay, interesting consideration and also question. So since this is tiny sensor is cheap, is there concern from a manufacturer on the cost in creating the data sheet?
Yeah, so that's something, we get into the economics of it, and we haven't fully fleshed that out. Like, what would a business model or whatever look like for developing data sheets? It's not necessarily clear what that would look like. We have spoken to several of the larger device manufacturers, and they said they would be very interested in developing their own data sheets, just, to show some level of social responsibility to the public. And then also it helps give them kind of, if they have more certification procedures, it gives them more credibility within the industry as well. And if you have enough of these willing to do it, then I imagine it would become more commonplace within the industry. But there have been a few projects similar to this, notably with IoT devices, which failed because they of that exact problem. They didn't really have sort of a sustainable business model or any reason for these manufacturers to come on board. But I think in more recent years, having social responsibility, it as a consumer facing characteristic has become way more sort of commonplace, and people care a lot more about products they buy than they did maybe 5 or 10 years ago.
Okay, so thanks. So I have a couple of questions. So I really enjoy your presentation. So again, thanks a lot. So one is about the model updatability. Do we expect for an ML sensor the possibility to update the model? And what does it mean for a datasheet perspective? Do we need to update also the datasheet when we have to update the model?
Yeah, this is a good question. And actually, I had this exact conversation just a week ago. But the question is, it's not very clear at the moment. Some people we've spoken to said they wouldn't want to update their models. I think that's maybe not the way to go. There needs to be a way of, for starters, there needs to be a way of doing secure updates. But another issue with this particular paradigm, which I didn't mention, but if you do have the capability to do model updating, you could potentially update the model to do something nefarious and no one would ever know because, they can't directly go in and probe what is happening. So, that's where in the aid of doing something socially responsible, it becomes socially irresponsible. So it's definitely a problem that we have foreseen. And I imagine it would have to be like some kind of updatable data sheet online that you go through and just update the characteristics. But the real problem comes in when you're doing the end-to-end performance analysis. How are you going to recharacterize that? Because, if I do an experiment with 40 people, do I have to do that every time I update the model? That's a lot of effort. Do I have to recertify with this certification body every time I update the model? And so these are great questions, and I'd say it's still an open question. Yeah.
Okay. So, and my second question is actually linked to that, but more about the future. If we think about this ML sensor, it's still made of a compute unit plus the sensor plus ML. So do you expect these ML sensors to be implemented through custom hardware IP or still use general purpose compute unit to allow model updatability of the sensor itself? So do we expect the proliferation of ML sensors through the implementation of custom hardware IP to meet, for instance, power, to have a very low power consumption for these sensors? Or do you expect to have anyway a general purpose compute unit to allow the updatability of the model?
Yeah, I think for the updatability, I'm not 100% sure, but I definitely see these devices as being highly specialized. For example, that's why we chose person detection, because it's a very commonplace application, but it's also very specific. And if you imagine, one thing that we would really like to see is the idea of having composable sensors. So in the same way that you have Google's Palm model right now, it can do multiple tasks and stuff. If you had the same thing with sensors where you could combine the functionality of multiple sensors that had very specific tasks to augment their capabilities, then you would end up with a kind of more general purpose sensing system. It's not clear what that would look like at this time, but I think that's something that would be really interesting to see in the future. Because if you look at the way that AI is kind of traveled at the moment, we had this narrow AI where you had one very specific application, and then you had an array of them. And now you have kind of language models, which is an abstraction above that, which allows you to access other models. And so I see the same kind of thing happening maybe in the sensor community with all of this AI stuff, where you have, a more general model, which then goes into these more specialized models. Does that kind of answer your question?
Absolutely, yes. So thanks a lot. So I'm going through the other questions we have in the Q&A tab. So a quick one. Do you think a pose estimation is possible with an ML sensor? So I don't know if you want to add something in terms of tinyML. Is it possible to develop or a pose estimation ML sensor with tinyML?
Honestly, I have never actually played with pose estimation, so I don't really know what the constraints are. So I'm just going to leave that one. I'm sure that person knows way more than I do about that.
Okay. So thanks. So other questions. Okay, what is your opinion on the future for tinyML? It seems like most of the teams in tinyML are working on image classification so far. What do you think about it?
Yeah, so if you look at the past year or so, there hasn't really been any huge advances in tinyML. It's more just been like, innovation in specific applications and use cases and stuff. I would say certainly tinyML is going to stay around just because of its utility, but I don't really see like ML sensors as supplanting it. I just see it as like a subset of tinyML. And I also see definitely like wearables is becoming a huge thing, and I could see lots of applications for doing that using tinyML. Although you could also argue that you wouldn't actually need tinyML to do that. You could just have edge devices. So yeah, honestly, I'm not 100% sure, but I definitely see a certain drive within an industry to have this kind of verifiability of devices and a way of stopping it from being like the Wild West of sensing and just having some level of credibility, basically. So yeah.
Yeah, and probably I can expand a bit because I think tinyML is not just about image classification, because there are also many applications in audio, also for speech recognition, but also tinyML is coupled to environmental sensors. We heard also today, and so it's the number of sensors that you can attach to a compute unit in the tinyML space are I would say a lot, and there are many possibilities. Of course, the limited number of memory and compute definitely put some constraints on what you can achieve at the end. Okay, so another question is about is there a difference between the data obtained by IoT device and the ML sensor you have talked about today? If there is, please help me understand further.
So I think this question is getting at the fact of I'm not 100%. Yeah, feel free to correct me if I misinterpret this. But in terms of like sending the data to the cloud, if that's what the person means. So the data that is being the raw data itself is not changing. It's the kind of utilization of the raw data, because the raw data is not going to leave the ML sensor. It's going to be abstracted in some way, and that could be in the level of like, some embeddings, or it could be a label, or it could be a number from, 0 to 127, depending on what you're doing. And so that would be the thing that the application processor has access to. And that thing is the only thing that has capability to send it to the cloud. The ML sensor would have such limited functionality that it could only do the thing it was supposed to do. And so in terms of what the data difference would look like, it would be that abstracted form, similar in the way to like privacy preserving technology. You can only get a very small piece of information, and that's the only thing you have access to. And I would say if you want to use that data, it's still useful for some stuff, like knowing what times of day people watch TV, or like, when they come in their house might be useful for a device manufacturer, without having, pictures of them entering their house every single day, something like that.
Thanks, Matthew. So conscious of the time, I think we can only take the last two. So about the, I don't know if you can answer, but in the deployment of these machine learning models for developing these ML sensors, was the quantization, I suppose intake quantization, involved in the process to optimize the machine learning model efficiency? I don't know if you can answer.
I'm trying to look for this question.
Is the fourth from the bottom. The question is more about the quantization approach. I mean, if you use intake for deploying this model.
Yeah, so we actually use the Edge Impulse framework to do that. And I believe that project and all of the data and training and stuff is fully open source. So if you go and check the paper or the GitHub page, it should have some information about that. If not, then feel free to email me, because I might have just missed putting a link somewhere. There's a lot of like websites and stuff going on around. So, but yeah, there was definitely quantization involved, some level of pruning, and I believe like hyperparameter optimization. But the underlying architecture that we used was a MobileNet V1 that was quantized to 8 bits, I believe.
Okay. And okay, probably we can take one more. for the other questions or comments, I think people also left the email address, so you can probably follow up offline. So does the person detection you have implemented differentiate between children and adults, or just people and not people?
Yeah, so this is a good question, and it goes into like data quality. So, for example, some of the images in the data set, I know I mentioned the horse example, but that was kind of just a funny one. But there was interesting adversarial examples of, like, you know, someone holding up a whiteboard in front of them, so you can only see their head and you can see their feet. And then the question is, like, would the device count that as a person or not? It's particularly difficult to characterize. And I would say for the children one, I don't know if MS Coco has a lot of data on children on it, which could be for, you know, various legal reasons or whatever. But yeah, this is a good example of where you would have bias towards a particular group of people. I feel like most people don't typically think of children being a group that has a bias against it, but I think in this case it would probably perform worse on children just because of the lack of examples of data within the data set.
Thanks.
But children do look like people, so it would probably still do okay.
Okay, so thanks a lot. I think we have finished with the questions. Of course, for those that we didn't take with a question, you can definitely contact Matthew to continue the conversation. So we're approaching the end of this session, and before we finish, I want to thank you again, because that was absolutely a very interesting presentation. I think this is also the question that we got today, and the number of questions is a reflection of the interesting topic you have presented today. So before we finish, we want to thank again the tinyML strategic partners for supporting all these tinyML initiatives. So thanks again to all of these the partners we have reported in this slide. So execute strategic partners, we want to thank Qualcomm AI Research, so advancing AI research to make efficient AI ubiquitous. We want to thank Sentience, making edge AI a reality. Platinum strategic partners, we want to thank Renesas. Renesas is enabling the next generation of AI-powered solutions that will revolutionize every industry sector. Atrios, deploy vision at the edge at scale. Sony. Gold strategic partners, so analog devices. Arduino, easily deploy your tinyML solutions with Arduino Pro. ARM, build the future of tinyML on ARM. Edge Impulse, the leading development platform for EdgeML. Infineon, driving decarbonization and digitalization together. Innaterra, neuromorphic intelligence for the sensor edge. Microsoft. SenseML, analytics toolkit suite. ST Microelectronics, which provides extensive solutions to make tiny machine learning easy. Synaptics, engineering exceptional experiences. And Silver strategic partners, AZIP, BrainChip, Green Waves, Gravity, IBM, ImageMob, Note AI, NXP, Polygon Technology, Kixel, Schneider Electric, and Silicon Labs. And this is the last slide for today with a copyright notice. So with this slide, we end this very interesting presentation, and I want to thank you everyone for attending. So, and definitely see you at the next tinyML Global talk. Bye-bye, and thanks a lot.